Welcome, everybody, and thanks for taking the time out of your day to come join us for this webinar. We're going to be talking today about Amazon DynamoDB, some of the key features and best practices, as well as some of the high-level design patterns. And we're going to walk through some of the technologies and actually demonstrate some of these features hands-on that in a live fire demos that you can actually see the stuff that we're talking about actually working. My name is Rick Houlihan. I'm a senior practice manager for NoSQL services at AWS, and I focus mostly on DynamoDB. I'm sure some of you are probably familiar with my content, others maybe not, and that's what we're here for, right? We're going to talk today a little bit about a brief history of data processing. Why are we actually looking at NoSQL technologies? Again, for those of you who've heard this before, just ride along for a few minutes because a lot of folks obviously haven't are new to this content. And we're going to get into an overview of DynamoDB. What is it? What is DynamoDB? Talk a little bit about the data modeling best practices for NoSQL in general and what it really means to manage your data as normalized versus denormalized schema. Talk a little bit about DynamoDB and the serverless ecosystem, and get into, some of the modeling and best practices for real world applications and showing you some actual real, technology demos and how this stuff works, right? So the first thing we want to talk about is the history of data processing. Why do we want to use this new technology? And really what it comes down to when you look at database technology over the years is there's been a series of innovations that have been driven by, this thing we call data pressure. Data pressure is the ability of the system to process the amount of data that we're trying to process at a reasonable cost or reasonable time. And when we can't do one of those things or the other, we're going to invent something. That's a technology trigger. And we've done this many times through the years. The first system that we were actually born with, the one between our ears, didn't last long. We needed to start writing things down, storing structured data in some way, to be able to build an enterprise, build business on top of. And that worked really well, ledger accounting and just kind of writing things down for many, many years, until the 1880 U.S. Census came along and a guy named Herman Hollerith was tasked with collating all that data, processing everything. And what it came down to was, it took him 8 years of the 10-year cycle for the census, which was obviously not going to work the next time around. So he invented the machine readable punch card and the punch card sorting machine. And the era of modern data processing was born. So, rapidly we started to develop new, technologies, new services, and new systems to be able to support those services. Things like paper tape, magnetic tape, distributed block storage, random access file systems. And the data sprawl in the 60s started to drive a team at IBM led by a guy named Edgar Codd into development of the relational database, right? System R was the first system that came out, did many things, right? It made data more consistent. It was very difficult to maintain all these copies and denormalized data on disks at the time. And it reduced the sprawl of the data, the cost of the data, and the ability of the enterprise to be able to store more data by deduplicating this data. It was tremendous value. Again, 40, 50 years ago, the most expensive resource in the data center was storage. And so this was a really effective technology. And the technology for maintaining the copies of data were not really available. But today, fast forward and, 50 years, and now the most expensive systems in the data center, the most expensive cost in the data center is really CPU, right? It's pennies for gigabytes to store data. We talk about terabytes, petabytes, exabytes of data today. So it's not about storing the data anymore. It's about processing it. And that's where the cost comes in. So when you look at NoSQL, it's about, basically processing data at scale. Now, when you want to use new technologies, and NoSQL is a new technology, they don't work the same way. And this is one of the biggest problems I see teams today. They kind of get into this, idea of I have this big data challenge, my relational databases are slow, I'm kind of sharding and partitioning my data to be able to handle this scale. And there's this thing called NoSQL that's supposed to do all this stuff for me, and it's great. Let's go get it. And they kind of run down this path. Well, the reality is that the innovators have come along and they've invented something. Here's this data pressure that we have, this big data challenge. And they've invented something, but the skill set isn't there yet. So people kind of go, they use it, they try to use it the same way, they use the old technology, and they have a miserable experience. And this is typical of the NoSQL kind of, path, and almost every technology path as it's introduced to market. You can't use it the same way you use the old technologies. You got to learn how to use it first. As those skills kind of become commodity in the market, the early majority lands, developers kind of become familiar with how to use it. The experience becomes a better experience, right? So if you find yourself talking about how NoSQL is difficult to use, I don't understand it, well, That's good that you recognize you don't understand it. Let's kind of learn about it. You didn't always understand how to use that relational database either, right? Remember that. At some point, it was new to you. So let's get into the new technologies and learn how they work. We'll have a better experience than trying to use these things the same way we use the old ones. And we'll explain a little bit about what that means when we get into talking about some of the best practices and things for NoSQL databases in general. So, why NoSQL? SQL is really about, why NoSQL? It's because SQL is really about that normalized relational view of data. The data is, well structured for supporting any kind of access pattern. It's agnostic to every pattern. And what that really means is it's really optimized for none, right? I have to kind of join indexes across tables and build these views of data. And as such, it kind of scales vertically. It works very well on a data set that's stored in a single container. It works less efficiently when data is kind of distributed across multiple containers. And it's kind of good for those OLAP workloads where I don't really understand what the access patterns are going to be, right? So that's kind of the category we fit that SQL works well in. But, NoSQL, on the other hand, works really well for OLTP applications, which are applications that have well-defined access patterns. If I understand the access pattern, then I can kind of model the data to kind of represent those instantiated views, the result sets of those queries, more or less, and be able to build hierarchical data storage structures that are more denormalized. They scale horizontally across multiple nodes, and it's really built for situations where the access patterns are well understood. Now, this is great because most applications today are pretty well understood patterns, right? I mean, this is what we're writing code for, because the code executes and it doesn't ask a different question every time it executes. It asks actually the same questions every time. And so having a database that's optimized to be able to provide the result set for the questions that your applications are asking is actually quite efficient. We'll get into looking at what that really means. When we talk about Amazon DynamoDB, it's a fully managed NoSQL database, right? NoSQL databases are great, but scaling the infrastructure behind them is not so great. And it's not something that you want to be involved with as a business. It's not really a core value that you want to develop. And this is really where I start working with customers a lot, is when they get into the scale aspect of things. Now, I also work with a lot of customers that are just getting started. And the reason why they want to use it is because, again, a fully managed system, I don't have to understand how to provide 5 nines availability. It's there out of the box. And for those of us that have tried to manage a 5 nines availability service, you know how hard that is. DynamoDB gives you that at the click of a button, and that's the kind of functionality that startups want for mission critical services, right? So again, document wide column database, scales to any workload. It's fast and consistent at any scale. We have workloads that execute in tens of millions of transactions per second and provide low single-digit millisecond latency. We'll show you some of that stuff in a minute. Fine-grained access control for all your data at the item level, the table level, the attribute level within the items. You can restrict processes to see certain chunks of data that you want them to, and others to see other bits or the whole items. And it's fully elastic. And this is one of the things that we'll talk about when we get into the performance characteristics of Dynamo. But there's no other database that works like this. It's fully on demand if you need it to be. You get whatever you want when you want it. You pay for what you use when you use it, and you don't even pay for storage, right, until you store items. Once you delete the items, then the storage costs go away. So there's no pre-provisioning of resources with DynamoDB, and it's what makes it really nice for the serverless kind of paradigm, that event-driven programming model that's becoming so popular today. Now, when you look at NoSQL databases, we talked a little bit about how they work differently. DynamoDB works the same way as all NoSQL databases, and that's one thing that you can argue back and forth with other people, but the modeling of the data is always the same no matter what the NoSQL database platform is. There's going to be some sort of collection of objects, right? In DynamoDB, we call these things a table. Tables have items, items have attributes, and not all the items on the table have to have the same attribute, okay? So this is one of the differentiators between a NoSQL database and a relational databases. The items on the table, they're like the rows from all your tables. You put them all into one place. In MongoDB, they'd call this a collection. In Cassandra, it's called a key space. DynamoDB calls it a table. Regardless, you're pushing items into objects into a repository, and all of those objects have to have a unique attribute to identify what this object is. That's the partition key in DynamoDB. It's underbar ID in MongoDB or DocumentDB. Again, it's a partition key in Cassandra. But this uniquely identifies that item within the table. So if I have a partition key only table, in DynamoDB, or I have a standard collection with no indexes in MongoDB, then this is that key value access pattern everyone talks about NoSQL is great for. And it is great for the key value access pattern, but the reality is that applications have a lot more complex access patterns than that. And if you want to try and push all the relational data that you have into these big blobs that can be described as key value data structures, it's a very inefficient way to model your data. We'll get into that in a minute. But the reality here is I want to create collections of these objects that are interesting to my application. And I want to treat these things more or less like the rows of the tables from my relational databases, right? You don't query all the rows that are related to each other all the time. You query subsets of those rows, right? You work with little chunks of the relational hierarchies that represent your data. And we kind of want to do the same thing with NoSQL databases, right? To be able to work with the data efficiently, we got to be able to get the data in and out kind of the same way. If I'm pulling big blobs of data to update small integers, I'm burning a lot of IOPS to do that. And that's a very common, anti-pattern in NoSQL. So when you hear people talk about, I'm using this database and such because it has large document support for like 16 megabytes, you got to look at them and say, well, why are you doing that? You shouldn't be storing data in big giant documents like that. And if you are, then let's talk about object stores like S3 for that data, because you shouldn't be, anyways. The anti-pattern is using the large documents. Anyways, what we want is to create collections of objects that are interesting to the application. So we have partition keys in DynamoDB. We can create a additional key, a compound key called a sort key, which gives us the ability to create collections of objects within these partitions. Right now, these partitions become more or less groups of items that are interesting to the application. In MongoDB, I'd start adding indexes to do this, but in other NoSQL databases like Cassandra, we also have the ability to add sort keys. Some even have much more complex sort key structures than DynamoDB, but regardless, what we're trying to do is create a collection of objects. And so if you think about it, we can start to model these one-to-many and many relationships by creating, containers full of things. If I have, let's say, a partition key, which is the customer ID, and I have a sort key, which might be a customer's interaction date, concatenated by the interaction ID. Customers do what? Customers make orders. They make payments. They get shipments. They make returns. They open tickets, right? But sometimes customer logs into a portal and says, what's my current, state of my interactions, right? With my service. I want to get my, landing page for the customer portal. I can query this table now and say, give me everything for this partition key for customer ID X with the sort key greater than date Y, and it brings back everything. Right? All of those rows from all of those tables, all in one query. And this is where NoSQL databases start to shine, against the relational database by creating these grouped collections, either on the table or on indexes, right? And then we can start to use range queries on those sort key operators to get filtered objects from those collections, essentially recreating the relational models, and we'll talk about this again in more detail, that you actually model in your relational databases. So that's what we'll do on the table in a NoSQL database. We'll add additional indexes. MongoDB uses indexes for almost all of this stuff, but again, it's always the same thing. I want to create, decorate these objects with attributes that I will group using indexes or partition key structures in interesting ways, right? In DynamoDB, we support secondary indexes on those attributes to essentially create additional partitions or collections of objects on secondary tables, right? Derivative tables, you can think of these things like, that are maintained when you update the objects on the table. Right, so you make a write to the table. If you have indexed attributes on that item, it'll be projected onto these secondary indexes, and you can choose how much of that item you actually want to project. I mean, sometimes your access pattern doesn't need all the object data. It only needs the keys to identify certain conditions of these items. Maybe you generate a list of items that have a key condition that violates a particular state, and then I'm going to go get those objects one by one and process them or whatnot. It could be the access pattern needs all of the attributes. It could be it only needs some of the attributes. Again, it depends on how much you need to get from the access pattern that you're indexing for, and that's a good way to control your cost, because you got to remember these indexes, just like all databases, when you write to the table, you write to the index. In DynamoDB, you project additional data, and that adds to the cost. Right. So if I project all, I'm essentially doubling my RCU cost every time I update the item. So just remember that when you manage your projections, you want to project the data you need to your GSIs. Scaling DynamoDB is just like all NoSQL databases. except that he actually works. Douglas Adams, if you're familiar with Hitchhiker's Guide to the Galaxy, one of my favorite authors, I love this quote, right? We all want stuff that works. We get technology instead. But DynamoDB is great technology, right? And NoSQL databases in general, they all scale the same way. DynamoDB gives you a fully managed service and a fully distributed backplane service that does this for you. But essentially what we're going to do is we're going to position these items across some arbitrary key space. In DynamoDB, we use the partition key attribute to do that. We're going to hash the value within that attribute, and that's going to generate some, hash value that we lay out across this logical key space. And as we scale the system, what I'll do is chop that key space up and start to distribute it out across multiple nodes. Now, when I query the key space, I'm going to ask for a partition key equality condition, right? And that tells me exactly which one of these partitions I need to go to, or I'm going to have to scan the table to find those items, right? So this is how NoSQL databases maintain that kind of fast and consistent performance at any scale, is by, essentially chunking up the workload, so to speak, across an arbitrary number of physical storage devices. DynamoDB is no different. One of the things DynamoDB does for you, though, is it manages all of that for you. You don't have to create shards, clusters, replica sets. All you have to do is tell us how much capacity you need, and we manage that under the hoods for you. So if you look at some of the kind of performance characteristics of a DynamoDB table, we have a billing mode called auto scaling, which gives us that kind of just-in-time capacity provisioning for your standard workloads, right? Your most workloads kind of follow the sun, or they have some sort of curve during the day in which the demand will increase gradually to a peak and then kind of ebb out to a valley. And when you have those types of workloads, this is the net effect of a system like DynamoDB over a legacy technology, a legacy NoSQL provider, or a relational database, where I have to kind of provision for that peak. So if you think about this workload that escalates over time and eventually hits a high peak and maybe ebbs off, in a relational database platform, all that area underneath the white line or the red line there is just wasted dollars. Hook the fire hose up to my wallet and let it go. With DynamoDB, much tighter provisioning allocation, of course, because we can kind of see the workload scaling. We have CloudWatch metrics we'll react to. We have some really nice tools out there for you to look at that one of my fellow SAs, Rob McCauley, actually demonstrated recently, and we'll show you in a second when we get into the workshop on how to kind of look at those auto scaling configurations. But regardless, it's about using what you need when you need it, and that's where DynamoDB just shines over any other database. You don't get that. The other thing DynamoDB gives you is performance at scale. Things that are counterintuitive. As we increase the workload against a DynamoDB database, we're going to actually perform better. And that's what this is, a synthetic workload. That's what this demonstrates, is that actually as we peak the workload here in reads and writes, I don't know which one's which, blues reads, oranges writes, and we're actually looking at the get latency here, and we're seeing how that drops as we start to peak into the millions of transactions per minute, per second. We're over 1 million per second here. And the reason why that happens is because DynamoDB is a fully distributed backplane service, and we have millions of request routers out there. I don't know, millions, thousands of request routers in a region for sure. But as you start to hit the table with millions of requests per second, all of those request routers become aware of your configuration data for your table, your security IAM permissions. There's a very short-lived cache. They'll look that data up every second or two just to make sure it's not too stale. But if you're hitting me with millions of requests per second, I'm not having to go look it up every time. And this starts to have an impact, right? The impact is lower latency overall for all your requests. And you can see that happening here as we drop from the 4 millisecond range down into the 2.5 millisecond range as we hit millions of reads per second. This is just not something you expect from a regular database. A regular database, as we start to peak out the workload, 95% CPU, you're going to see the opposite, right? You'll see the latency spike. You'll see the server start to go sideways. Eventually, it just goes offline. And DynamoDB doesn't actually go offline. When you actually ask for more capacity than you have provisioned in DynamoDB, DynamoDB has this thing we call a burst bucket, which is 5 minutes of unused capacity. And this is Snapchat's a well-known DynamoDB customer. Super Bowl Sunday. This is 2019 Super Bowl. They hit about 12 million requests per second. I think they peaked out somewhere around there. Their provision capacity during the day was about 5.5 million steady, because that was the floor of their auto scaling algorithm. We typically recommend customers do this on event days. They expected a lot of traffic. If there's a big event day, like a Prime Day, a Super Bowl, something like that, then go ahead and set your auto-scaling floor up to what you would expect the daily peak to be, ride through the event, and then drop it back down to your normal operating levels. There's no reason to have to challenge the system, right? If you know that it's coming, and maybe set your ceilings up above that so you'll scale up if you get too much traffic. In this case, you can see what happened. The table just flew up above its auto-scaling floor. But for the 5 minutes preceding, it wasn't using its full table allocation. So, we'll take all that unused capacity and apply it to your spikes, to your peak loads, to keep your system running, even though you're asking for, a transient spike in workload that exceeds your provision throughput. What happens with a relational database when you do this, right? It's dead. It's going to be on the floor. It might actually be sideways and need life support at that point when you run it to this type of workload. Who knows what happens, right? When those types of systems run out of infrastructure capacity. DynamoDB has more capacity than you need whenever, so there's nothing to worry about that. Now, on demand, that's another workload capacity mode that you can look at for your workloads. This gives us a whatever you need when you need it within some limits. You'll always be able to allocate at least twice as much throughput as you've previously peaked to on the table, but you're going to get it instantaneously, right? Auto-scaling takes, 10 to 12 minutes. Got to read those CloudWatch metrics. We've got to respond and react to what's happening and then apply new allocations to the table. So on-demand happens right away, but it's more expensive, right? So it's good for workloads that are very transient, right? Spiky workloads where you don't really know when it's coming, but you need to have the capacity when it's there. We had lots of customers that were provisioning for that peak workload because they couldn't, throttle anything while they waited. So they were paying a lot. And that's not something you have to do anymore with on-demand. So depending on the workload can make a lot of sense for you. And I always recommend people kind of start there and see what it looks like after a week or so, after a couple of weeks. And then you can use that previous those previous metrics from CloudWatch to configure your auto scaling. The other thing you get with DynamoDB, we mentioned it a little earlier, is 5 nines availability right out of the box. If you drop a DynamoDB table into a single region, you get 4 nines availability. If you click the button, enable global tables and replicate your data to another region, we're going to give you 5 nines availability, and that's an SLA guarantee. I know a lot of services out there, and I've actually participated in all these services over the years where I've had to question, do we really have 5 nines, even though, of course, the RFIs and RFPs that we're responding to are all saying, you must be 5 nines. What did the vendors say? They all say we're 5 nines. Are they 5 nines? How do they measure 5 nines? We measure it. It's up there on the console for you, and it's an SLA guarantee. So, those service credits are automatic. So it's not something that's, we have to, dole out. It's certainly, we maintain this service as a 5 nine service. All right. So before we get into the demos, I'm going to talk a little bit about data modeling. In NoSQL, we talked about relational data a bit and how you sort of lay that data out into the tables. But, it really is about relational data. When we talk about the data that your applications are using, there is not an application service that I've ever built that I hasn't involved using relational data. It doesn't matter if it's social networking, IT systems management, document management, anything you're trying to develop for, the data has relationships. And if we can't model those relationships in the database, then the database is kind of useless. It really is. And when you start looking at NoSQL databases, it's all about how do I model those relationships in the data. We explained a little bit about, this indexing, and we'll talk about and demonstrate how powerful that can be when we just break down a simple product catalog, right? This is kind of that relational data structure we're very familiar with. We have the one-to-one relationship between products, books, albums, videos, one-to-many between albums and tracks, many-to-many between videos and actors. And this gives us, the ability to run any query. You pull up any list of products using, but multiple queries. In a NoSQL database, maybe a different approach, maybe a more naive approach. I wouldn't necessarily recommend doing this, but this is actually for this data structure, probably not such a bad idea, is to create these kind of hierarchical data structures as documents, not necessarily, individual rows. We'll look at what happens when we treat all this data as individual rows in a second. But this is obviously a better data structure to retrieve all my products. For that access pattern or get any given product, because I always need the hierarchy of data. So I would create these types of hierarchical documents and say, get me this product by ID, Get me all the products. Just scan the table. Right? I don't have to write queries. What happens on the tables when we load the data in and look at the time complexity of those queries, it becomes apparent why NoSQL databases start to shine, right? So if this is treating all the data as separate rows, we're going to put all the data on different tables, and we're going to start to look at that time complexity. You can start to see as we join more and more tables into these queries, the time complexity starts to increase exponentially, right? And this is not something that gets better. I mean, this SQL is pretty rudimentary stuff. If you get into production databases on a lot of complex schemas, they're going to look a lot worse than this. And on large data sets, that really starts to chew you up, right? Now let's take all those rows and we're going to stick them in. Again, another naive approach here. I wouldn't necessarily recommend modeling your data this way, but to emphasize the point, we're just going to take all those rows and stick them on the same table. What ends up happening here is apparent. Now, all of a sudden, we have partitions. Partitions are groupings of objects, right? The one-to-one joins, I just kind of created one object because they're the same. They're very, very small objects, so a single item is not a big deal. As we start to, look at these one-to-many joins now, hey, guess what? It's pre-joined. All those rows exist in the same table. If these are all small objects, but if they were different objects with different access patterns, you can start to see how the efficiency drives here. If I need to update a single song item, I don't have to update the entire album. I only update the song item, right, within the album. And this gives me a lot of flexibility when I'm accessing the data, right? But I mean, for the bulk access pattern to get me the album, there's no join, right? The data is kind of pre-joined. It's all on the same index. Essentially, that's what a join does, right? It joins indexes. If you're joining on attributes that aren't indexed, then that's probably not a very good query. So if I put all the objects on the same index, I get a lot of flexibility, right? And so this is demonstrating that, right? Select the movie by movie title. This is our many-to-many. If you look at that kind of graph relationship that a many-many construct gives us with that mapping table, those are kind of the edges. I kind of loaded the mapping table into the movie partition. And on those mapping edges, I added a little bit of the data from the actors row, their gender, their birth date, right? Things that are kind of, that's data that doesn't change, right? I don't have to worry about, that data updating frequently. And, even if the data updates intermittently, then we've got some systems to be able to handle that now. Streams and Lambda can guarantee those updates. But this is a kind of a directed graph, right? If I look at the movie, it knows about its actors. The actor doesn't know much about the movie. But if I go and I flip the keys on the table into an index, right? So now the index has a partition key, which is actually the sort key of the table, and the sort key is the partition key from the table. You can kind of see how we can see a whole bunch of different relationships expressed here. Like I want to get all the books for a given author. I want to get, all the albums of song that has been on, right? I mean, I want to get, hey, all the movies that an actor's been in. This is the other side of the many-to-many. And I haven't denormalized any of the movie data here, but you easily could depending on your access patterns. And if that's like IMDb, I might want to see that. I might want to see, hey, here's the movies he's been in, the roles he's played, the summary of the movie, and I'll click here for more, right? So that's just kind of traversing the graph, right? If I want to go and see all the movies that directors, directed, I can see all the albums that a musician has produced. And again, as I start to extend this concept into the extended attributes, right? These things can have items can have state, give me everything in a given state, give me every given state in a given area or whatnot. You can start to see how these relational access patterns can be expressed without having to denormalize the data very much, right? When we get into many relationships, depending on the nature of the relationship, we probably want to do a little bit of denormalization. But again, if you have things like, standard access patterns, standard relational queries, we can absolutely, express those relationships in a NoSQL database. It's kind of like there is no such thing as non-relational data. That's what I like to say. If you hear me, if you've kind of listened to me for a while, I don't say that much. All right, let's talk a lot about complex queries. Complex queries are things like counts, sums, aggregations, the types of things that, are hard to do with NoSQL, right? Because they're kind of computed on the fly, right? And one of the things we learned at Amazon, we started doing these types of queries, right? Give me all the downloads for a given song. Well, I don't want to go count all the download events every time someone comes in and says, give me the download. Somebody goes to their UI and it shows a counter for downloads for a given, track in Amazon Music. Of course not. So we have some summary data that gets kind of, scanned and compiled, and then updated on a regular interval, and that's what you see. And that's kind of the same way we do things with DynamoDB. With DynamoDB, we have a built-in change data capture pipeline that we can automate these types of activities, and that's what a lot of people do. And there's a lot of really good use cases for this. All the data events, all the writes, the updates, the inserts, the deletes, any type of data change event hits DynamoDB stream, triggers a Lambda function, and we can do those things like maintain summary aggregation reports, just right back to an item on the table that contains all those summary metrics. Now, every time someone wants to come in and say, hey, what's my last 30-day running total for X? That's what your Lambda maintains. So I just select the item. I don't have to compute the result. This is a really, really fantastic way to do this. At the same time, we can start pushing that data out to third-party systems or external systems like Elasticsearch for higher level indexing functions. If I need full text, geospatial, or index intersections, things like this, I can push subsets of my data into Elasticsearch to support those access patterns. We can put the data into Kinesis Firehose, roll it up into Parquet files, and shove it into S3. This gives us the ability to query the data from Athena. I like to do this a lot when these running aggregation workflows, as I'd like to kind of maintain these running aggregations, and then at the same time, have this audit trail event flow, because I can always query the Athena, data at the end of the day, and I can make sure that my summary aggregations are completely accurate. Because one thing about Lambda is it's guaranteed at least once execution. So if a container does fail, the Lambda function might, re-execute on the same data once or infrequently, but it can happen more than once. So it's nice to have the audit trail, because I could just write the queries for the summary the summary against the data, let that execute at the end of the day. It's going to take a while to run against that S3 data, but when it comes back, I can just sanity check my summary aggregation reports to make sure that nothing's off. If I need a fine degree of accuracy, that's a good pattern. Notify third parties of change, execute downstream workflows. This is, again, it's code, so you can do anything with code, and it's all up to you. DynamoDB streams and Lambda is completely managed behind the scenes. It's nothing you need to worry about. As your table expands, so do the stream processors. As the workload on the table expands, the stream processors will scale up and down behind the table. But there is one thing you need to worry about, is the Lambda execution timeline or timing, right? If the work that you're doing within your Lambda functions is too much, then they start falling behind the stream. And if the stream activity is constant and steady, then eventually you're going to run out of stream buffer. And after 24 hours, you start to lose data off the edge of the stream. So, those what they call iterator age. We want to make sure that the iterator age in your Lambda functions is relatively low or manageable, and that if it's increasing, that it's through bursts and not through straight, steady activity. Now, you can increase the parallelization of your Lambda functions, so that if I have a function that's a little heavy, I can run more concurrency and execute more batches as concurrent operations, up to 5. But honestly, my advice is, if you have work that's slowing down your Lambda functions, then let's go ahead and offload that and pass it off to a step function, or push it into SQS or something like that, and let it execute asynchronously, not in line with the Lambda function. Because again, that iterator age, you just don't want it to get too old. Otherwise, the processing you're trying to do is stale, right? And that's no good. So this is kind of the overview, right? The serverless app, the front end, right? We come into the system. DynamoDB is the backbone. It's where all the data stays, gets stored for a serverless app. But on the back end of DynamoDB is another ecosystem of tooling that gives you an amazing collection of functionality that people can use to extend the application, so to speak. So, it's like DynamoDB at this point, it's more than an application, than a database. It's a data processing engine. There's a whole set of operations that can occur behind the data because of this change data capture processing pipeline and that at least once execution guarantee from Lambda. And we're going to demonstrate some of that as we get into the next portion of our presentation. All right, so that's what I've got for you from the presentation today. We're going to talk a little bit about some of the functionality now, get into some demonstrations, some hands-on. I'm going to show you guys some code. I'm going to show you guys some workflows, some exciting new functionality around Particle and the new APIs, and actually demonstrate why. Why is it that this single table design that we just talked about is so much more efficient than doing things the way we used to relationally, right? Why shouldn't I put all my data on many tables, right? We're going to demonstrate some of that stuff for you. Again, we're going to talk about that in a minute, and let's get into the demos. All right, so for our first demo, we're going to take a look at the Particle API. Particle is a SQL-like construct that is provided for users to access their DynamoDB tables. It gives you a familiar syntax to work with your data. It doesn't necessarily support all the functions of SQL, right? Like a relational database doesn't, NoSQL does not join tables, but it supports all the relevant operators, and it removes the requirement of the developer to understand the intricacies, so to speak, of the DynamoDB query API, right? With the low-level API or the document API. Users are responsible for determining which actions to opt to run, whether it's a get item, a put item, or a query, or a table scan. With the Particle API, it works a little differently. You give us some query criteria. Based on those criteria, we kind of look at it and say, hey, you gave me enough. I understand what I need to do, whether it's going to be a query or a get item or a scan, depending on what you give us. The request router is going to make a decision about what operation to run, right? So with this comes a couple of caveats, right? Sometimes maybe you don't necessarily want things to happen, right? I don't necessarily want table scans to occur if I don't give it enough data in my query. I'd rather it just fail. And so we're going to show you how to do that. So let's take a quick look at that table that we're going to be working with. This is a data table that contains synthetic stock trades. I use this for a lot of my demos, right? We're going to actually use it a little later when we talk about global tables and export to S3 and whatnot. We're going to push this raw data out there and take a look at how we can get at it. But for this demo, we're really just going to be querying the items on the table. We're going to be looking for, what is Particle doing when we make these queries and what type of operations are running. So the first thing we want to do is set up a user policy, for our Particle process, right? Whatever's running, we want, of course, least privileged access. In this case, we're going to give it, access to the Particle API only, inserts, selects, deletes. We're going to assume this is maybe a workload that's running in our production environment, and these are the operations that we need access to. And so let's go ahead and switch over to that client view and see what happens when we actually execute some of these queries, right? So as you can see here, we're now a different user. I'm the demo user with our policy that we just defined, and I can't even see the tables, right? I don't have list tables process or privileges. I only have Particle privileges, right? So let's go ahead and run a simple Particle query. We're going to select star from the data table where our PK is equal to some string value and our SK is equal to some other string value. And we'll grab those in a second here. One thing about Particle, remember, syntax is important. I need my and statement there or it's going to fail. Quotes go around entities, things like tables, attributes, whatnot, double quotes. Things like values, single quotes. And it's very important because it'll crash if you don't, it won't parse the queries properly if you're not surrounding like your string values with those single quotes and your entities with those doubles. All right, so let's grab the data we need. This is our partition key, S3-97. And our sort key is going to be hash, is it T1768? 1768. Okay, so we should have a transaction on the table with that particular partition key and that particular sort key. And with these query conditions, I'm giving Particle enough to know that it should run a get item, right? Because I'm giving it both a partition key equality condition and a sort key equality condition. That's great. That tells Particle, give me that item. So select star from. Need to add our from condition. There we go. We add from, and we should be able to run this now. There we go. Okay, so we got our item. This is the item we expected to see, and we've got a exactly what we expected, right? The partition key S43 and hash 97. And again, this is a get item. If I remove the sort key condition, I can force it to run a query. In this particular case, if there was more than one item in this partition, it would bring back more than one item, but there's not. There's only one item, so it only brings back the one item. However, if I provide only the sort key condition, then I'm not giving it enough information to know whether it can run a query or a get item. So it's going to default to a table scan. And let's see what that looks like. It actually brings back the same item, but we got a little thing here that says, hey, query execution did not finish searching all the items. What does that mean? It means it brought back more than a megabyte's worth of data. The item we were looking for happened to be in that megabyte, but as you can see, this is a little tiny item, and I just burned a megabyte worth of RCU to get it. I can scan the rest of the table. It doesn't bring back any other items. This is not the operation we want to execute, right? I would rather this query fail than burn that kind of RCU, right? So how do we make that happen? If we go back and take a look at our policy editor, we can see what kind of tweaks we need to make, so to speak, to our policy to actually ensure that scans don't happen. One second. Grab this policy condition, and let's edit this policy one more time. I'm going to go to the JSON view, and I'm just going to add a deny operation here, right? And the deny condition is going to be on particle select, which is odd because, again, I'm allowing particle select, but what I'm denying inside of particle select is a very specific operation, which is the full table scan, right? When the full table scan condition is true, then that operation is going to get denied. And so let's see what ends up happening if I review and save this policy change. We can now, I got a couple old versions we need to step on. And so now this is my new policy here. Give it a second to propagate. But essentially, I'm allowing this process now to insert, select, and delete. But select is only going to work when full table scan is false. If full table scan is true, then that's going to deny that operation. Okay, so let's see what happens when I go back over to the console and look at that and run our query. So this is the same query again. We completed before. We brought this item back. We paginated it across. If I run now, it should come up. It's error executing the command, right? Access denied. We don't have authorization to run that scan. So this is how we're going to limit particle operations from executing procedures that we don't want them to, so to speak. We can give them table scan, deny, insert, select, delete operations specifically, and conditions on those operations accordingly to control what the particle API is doing. So don't be afraid of it. Actually, I'm loving it more and more. The more I use particle, the more I'm embracing it. It has a whole bunch of functionality in there that's not necessarily available in the document API. Batch execute statements with multiple conditions is probably the number one thing, right? In the document API, when I do a batch get, or I can't add multiple conditions. I can't run multiple queries as a batch. In Particle, you can. So there's a lot of functionality there for you. And with this fine-grained access control, you can govern what's happening at a very granular level. So great technology. And let's take a look at our next demo here. For our next demo, what we're going to do is take a look at a streams lambda aggregation. And we're actually going to be doing two things. We're going to be aggregating the items that are coming into our trades table into a summary table that's going to be by security. And the other thing we're going to be doing is pushing that raw data out through a Kinesis Firehose stream into an S3 bucket. And we're going to be able to run Athena queries for our audit trail and validation of our aggregation function, right? So take a look at the data again. We're using the same table that we used the last time. The data table. As items come into this table, these are individual trades. They contain information about the trade. What was the security? What was the type of buy or sell? How many shares? What was the timestamp, right? What region it was generated in, and what the price was. So that's all the information that we actually want to capture is raw data. And the way we're going to do that is by, again, exporting the data with Kinesis Firehose, using a glue catalog schema definition to be able to format the data into a Parquet file, drop it into S3, and then we'll be able to query that data with Athena using straightforward SQL to get those audit trail workflows, which is a really good workflow, right? Any of the change data on your table can export into an S3 bucket and be available this way, for those audit trail workflows. All right, so let's take a quick look at the glue catalog definition here. AWS Glue is really a schema definition tool. You can scan existing data repositories and build schema. You can logically define schema manually. In this particular case, since the data doesn't already exist, it won't exist until we actually push it into the catalog. We need to define the schema up front. And so that's what we're going to do. We're going to have this stream proc DB. We're going to define a single table inside of that database, which is our trades table. And if you look at the definition of the trades table, it contains all those fields we just talked about, right? What is the security? What is the type of the trade, the shares, price, region, timestamp, so on and so forth. And really all this is a schema definition. It's just telling whatever system is referencing Glue that the data catalog that it's trying to build using the raw data that it's trying to process should look like this. Okay. The next thing we want to do is configure that Kinesis Firehose, right? Firehose is all about delivery streams, pushing the data that it's receiving into a destination. It batches these things up and drops things in batches into that your particular location. In this case, it's a S3 bucket. And I've got multiple stream processors defined because my account uses default limits for the Firehose. So I didn't want to go through the hassle of increasing those limits. So I just spread the data out across multiple Firehoses to increase the bandwidth or throughput of the system. These limits can be increased on a per stream basis. So you don't necessarily have to run multiple streams. But in my case, I went ahead and did that. It's a pretty straightforward process for configuring a delivery stream. Essentially, all you're doing is telling it where to go and what catalog to use, and that's essentially what this does. It says use the Glue catalog from the Oregon region. We're going to transform these into an Apache Parquet file. We've got the stream proc DB is the database we're going to use, and the table format, the table schema that we're going to use is the trades table that's defined within the stream proc DB schema, and that's it. So once you've got that, you tell it what location to put it into. We've got an S3 bucket defined for the stream proc DB, and we're good to go. So at this point now, I've got a whole bunch of data streams defined. We're going to be spraying the data across. I've got the Firehose set up for grabbing the individual or pushing the data into those Parquet files in S3. And now what we're going to do is take a look at the lambda function that we're going to be running here, which is not terribly complicated, but it does quite a bit of work. If we look at the functions that we have defined in the system right now, I've got the stream processor function is the one we're going to be working with. This guy's triggered off of the DynamoDB table. And if we look at that trigger definition, it's telling us it's coming off the data table, right? So all the write operations off of the data table, every single time an insert, update, delete, any kind of write operation occurs on that table, it's going to fire this stream processor function. And the stream processor function, again, it's not complicated code, but it does quite a bit of stuff. So let's go ahead and just break it down bit by bit, right? First thing we want to do is instantiate an instance of the document client for DynamoDB. We're going to set some configuration parameters, right? We want to know what region we're in. We don't want to process records from any other region. So this is a pattern I use constantly with global tables. If you have master configuration, you always want to tag those items with a source region. And why do I do this? Because global tables doesn't recognize the writes that are coming as replicated from other regions. It just executes the same process it executes on any write to the table. And so if you don't want to process the items that are generated or updated in other regions, then you'd want to tag those items with a region label so that to drop them. And that's what we're going to do in this logic. If it's not the region that we're expecting, we're just going to drop the items. Next thing we want to do is instantiate our Firehose client. This is for sending that data into S3. And a couple of things we want to do with the Firehose client, eventually tell it what stream processor and whatnot to build. But that happens inside this handler function. Okay, so the handler function fires on every single record that comes into the system. And we're going to declare some global variables here. And one of the things that's important is telling us which stream processor to use. Remember, I talked about my Firehose configuration. I've got 10 stream processors, stream processor 0 to 9. Essentially, this is what I'm doing on every one of these Lambda invocations. I'm going to use a different processor. So as we start to scale the system, I'm going to be spreading that data out across, those 10 Firehose streams. And then the only thing I need to do, again, build the container for the write. Essentially, it tells it what stream to go after. It tells us, the array of records to push onto that stream. And that's the parameters object that we're going to push into the Firehose put. As we get into the actually processing the records, this is where we're going to start to look at things we care about, right? If it's not a insert, it's not coming from my source region, then I don't care about it. Just drop it. This processor is going to ignore those items. If it is coming from the source region I expect, if it is an insert, then I'm going to, skip anything that's not actually a transaction. So I know that on this table, all I'm doing is inserting transactions, so no problem. But to future-proof this function, just in case down the road I start adding additional item types, I just want to make sure that I'm actually, processing the records that I want to process. Once I know that's a process, that is actually a transaction, a stock transaction, then I'm going to go grab all of those top-level metrics from it: the price, the share, the region, the type, security, timestamp, all of that stuff. We're going to push that into a security counter, right? As Lambda processes records in batches. If I have high velocity trades happening on a single security, I'm going to end up getting dozens or maybe hundreds of those in a single batch. And to be able to kind of reduce the pressure on the summary table, I kind of want to summarize all those items inside of the Lambda function before I push a single update to the summary table. All right, so that's what we're doing here. If this is the first time I've seen a trade for this security in this batch of items, we're going to create a new counter for that security. And then what we're going to do is just summarize buy shares, buy total, buy orders, and all that by each security for buys and sells. And then if we're processing the item, then we're going to push it onto the Firehose container so that we can push it to through the Firehose stream into S3 for our historical queries, right? So this is kind of, again, this is the method that does the big work. Again, all this code is going to be available for you. I'll post a link to the GitHub repo where you can pull this down and play with it yourself. But this handler function is where all the work happens inside these event records for each loop. This is where the summarization happens. Once we summarize the records, we're going to go ahead and batch them up, wrap that Firehose put into a promise, and then we're going to start to build our update expression for the summary items. Right, we're going to update the totals for the buy, sell, trades for each individual security. They all have the same update expression. They just use different parameters. We're going to initialize counters for the next day. Right, this is important. If I'm maintaining a summary item and it has 30 days worth of trailing totals, well, tomorrow I need to have the counters so I can start incrementing them. So on every update during the day, we're going to set tomorrow's counters to 0. That way we know they're going to be there when we start processing items for tomorrow's trades. And then it's just a matter of getting a promise for each one of those updates. Once we push all those promises onto an array, we're going to await those promises. When everything comes back, hopefully true, we're going to move on and we're good to go, right? So this is, again, the kind of workflow we're going to go through for two things: summary aggregation, which is where we're pushing all those stock trades into those summary counters, and historical audit trail queries, where we're pushing all the raw trade data out into an S3 bucket that we're going to be able to query later. Okay, right? And let's take a look at what that actually looks like. If I go into the Athena console, I can actually see what's been happening here as I run this scenario over and over again over the months. We've stored all that historical data from all those synthetic trade transactions. And what I'm going to do here is I'm actually going to go into the AWS data catalog, right, which is our glue data catalog. I'm going to pull the stream proc DB. So let's take a look at what that looks like here when we go run that query. If I go and execute against the trades table, you can see it takes some time to come back. It's not the snappiest query performance because, again, it's it's Parquet files, S3. Athena is really a map reduce engine on top. So it took a little while to get the data, 2 seconds or so. We scanned through about 29 megabytes of trade data there. We got a little over 3 million or so trades that have been recorded, 31 million trades. Okay. So what's nice about this now is I can go do all kinds of stuff. I can get my top in. This is just to run whatever SQL you want. You can run your top in against your trade volume by security. This gives me my top end buy, sell, volume by volume. And again, these are nice ways to be able to go out there and look at, slice and dice the data in interesting ways that you don't necessarily run at high velocity. I don't need to necessarily run low latency queries against this data set. It's an extremely useful way to be able to run those audit trail queries, right, that we all need. I want the historical data, but I don't want to have to pay to keep it online. Most of those audit trail queries aren't things that last or that run at high frequency, right? They might run, a couple times a month. Somebody needs to come in and do some troubleshooting, maybe a couple times a day, and it's not really a real-time workflow here. If it takes a second or two to get that data, in this particular case, it took us 3 seconds to scan through about 100 megabytes of data to produce these top-end aggregations, that's just fine for an analyst at the end of the day who wants to run and get some numbers, right? This is not something that needs to run in milliseconds. So really good workflow here that we just demonstrated, be able to take that change data through the streams, CDC pipeline and do two things. Aggregate the data back to the table. If we go back and look at that summary table, we can actually see what those summary items look like. This is the data table that contains the summary information that we built. And you can see, those items essentially by security, partitioned on security ID, and they give us that daily 30-day trailing, right? In this case, we built a couple days worth of trade data, but as you can see, it gives us exactly what we build in our stream process in our lambda function as we, update our buy shares, sell shares, buy totals, buy orders, whatnot. When we go back to our summary table in our DynamoDB, we see exactly that data aggregated and pushed in on a daily basis by security. So again, aggregate by security, push data out to S3 for audit trail, change data captured pipelines into S3 for audit trail queries, really good workflows for your Lambda functions. And, just so that you guys have the code available, there's a nice repo up here that was put together by one of my peers, Rob McCauley, and this code lives up there. I'll post this in the chat. Folks can go ahead and take a look at this repo. There's a couple of things in there we didn't really go over. Cost modeling for table scans versus index queries, auto scaling calculator, whatnot. The code that I was running today to do all this was in the table loader, and it includes the Lambda function and whatnot that I was just going through. So if you want to go ahead and pull that stuff up and kind of play with the code yourself, it's all up there for you in this repo. Again, I hope you guys got something out of today's session. I'm going to be available here for the next 20 or 30 minutes if you guys have questions. And thanks a lot for taking the time to watch the session. If you want to hit me up on Twitter, my name is Rick Houlihan, and this is my Twitter handle. And again, thanks so much for hearing this session.